Too much time to work on this the past few days, but I did spend some effort to basically work on optimization. So I was having really bad hitching when we would spawn in galaxies and things like that. So I figured I would review kind of the changes to this class and how I managed to do that, which is still probably not perfect because I still have a garbage collection hitch that pops up every now and then. But first, we can kind of see what is going on, and then I will talk about the code changes and like the next steps, which is basically to take all this logic. So the galaxies are what gets spawned in all the time, whereas the universe only gets spawned in once. So I've been focusing my efforts on optimization there because it's just easier to test. But we do want to eventually move the same kind of system to the universe actor as well because that'll speed that process up somewhat. So yeah, let's spin this up, take a look. I still need to get the proceduralization back in. Like my material is just whatever the material instance says it is for the volumetric component, but that is relatively minor. Uh, like that takes like 15-20 minutes max. Okay, so when I start up, it will spawn in the universe, and it will take in a minute because the universe is not optimized yet. But even so, it would still take a little bit of time for that. But once this spawns in, we have our nearby galaxy here with this specific universe seed. So what I've been working on primarily is the spawning and destruction of these galaxy objects. So we can see that that just got destroyed. So if I were to fly back over here, I want it to like basically not lag the system while it spawns in. So you can see there, it respawned the galaxy. If I were to go over, and it's still not perfect, because it will still occasionally have a little hitch, but it's much better than it was. So here we go. We go over to another one. We could fly into the middle of it, decrease our uh, parallax speed scale to the point where we're moving at like there's so that just happened. That was the garbage collection hitch that I haven't quite figured out yet. There's something causing the garbage collector to spike occasionally, and it is like maybe every 30 seconds or so, but I don't think it's related to my code. It's probably related to my Niagara or garbage collection settings. Um, but anyway, we have our volumetric spawn in. We can see like our individual stars in the galaxy that we spawned in. I go, I'll go to one here. There, oh, oh, there's one. Um, so yeah, this seems to work pretty well. The other thing I was having a problem with is because the way we were controlling the spawn in of these was pretty naive. And because it takes anywhere from like 1 to 3 seconds to actually spawn this thing once you start initializing it. Um, if you flew by a point really fast, you would both immediately lag while it was generating, and if you had exited the point to where that galaxy had been destroyed before it finished its initialization process, it would load in the particle system in the wrong place and scale, and you wouldn't be able to get rid of it from that point on. So now, if I fly, let's fly past this one at speed. So it tried to do it, but it stopped. It exited early. It will basically short circuit if it's like if you leave the area before the galaxy generation is done. So now we don't get that same hitch of like flying past at high speed. If I even slow it down, you can see that like we're basically not ever spawning it. There's the garbage collection hitch. I'm not sure why that's happening. I'll have to do some more investigation on that. But that means that we can safely fly through our system without locking ourselves up. We can, if we're flying at like a reasonable speed, then it should spawn in before we would be able to see it. So like here's one. Oh, there it is. It spawned in. I also decreased the number of stars I was generating. We may be able to ramp that back up. Right now it's generating anywhere from 100 to 250,000 stars in a galaxy, which is obviously not real life numbers, but at the same time, I don't think we necessarily need real life numbers for this. Just needs to be like convincing. And again, like I don't have any kind of proceduralization going on the stars themselves or um, the galaxy volumetric itself right now. It's all just statically defined in the material instance. Like we're spawning the material instance, so we have the ability to customize it, but that's why the colors on these are all the same and the noise patterns are all the same. The only thing that changes is the underlying density map that volumetric system is generated from. So yeah, we can fly to anywhere in our galaxy. We can look around. We have our night sky. Um, we have our universe volumetric here, which I do want to change the universe volumetric to be a little bit more uniform rather than concentrated with like the cluster density. But we're going to kind of address that when we go to edit the universe itself and kind of update all this stuff. And the hue shift here that you see at like incredible speeds, this would be extreme intergalactic speeds that we're traveling at already right here. If we go faster than that, obviously we're traveling like you would never travel this fast in the game. But the whole reason I'm doing the color shifting here is because I want the skybox formed by the universe you're in to be different depending on where you're at. So, like, I want you to have um, a gas cloud generated for the galaxy that will contribute to kind of the colors of your night sky. But also, the universe itself should, I don't want it to just be a static color so that it always looks the same no matter where you're at. So I have a little like position noise based hue shift going on with the galaxy um, or the universe volumetric effect that I don't have in the galaxy one. But anyway, so that's how it works. It's not perfect, but it's definitely much better optimized than it was. You can see there it took a little bit less than a second to initialize that, which is, and there's the garbage collection hitch that I still have to figure out. But it's nice to be able to fight through this and not have to worry about like locking up because I accidentally flew past two galaxies too quickly and the whole system lagged up. So with that said, I can kind of go do a review of the code changes that it took to get to that. So first we'll take a look at the header. We have an initialization state now. This can be initializing, ready, or destroying, and we use this to short circuit our initialization processes in case um, in case the galaxy is being destroyed before we finish initialization, and that's what allows us to fly past them at high speed, trigger the event, but like not finish it. We have our universe pointer. This is a pointer of the universe actor. I think the only thing we use this for is speed scale. Um, yeah. So this is used to calculate the position that it would spawn in. Um, if we have a universe reference set and the universe, if we have a reference to the universe set, we use the universe's speed scale. Otherwise, we use our own speed scale in the parallax calculation. So that's so that we can change our speed scale at one point and have it propagate through all the galaxies that have been created. So when we create this galaxy, we will need to set a reference, or not a reference. We'll need to set a pointer to the universe that spawned it. Going back here, we have our octree. This is our data model. This contains the position and like voxel data for all our stars. We have a series of initialization parameters. These are used as a way to externally randomize basically our default parameters that are used to populate our data and our octree and things like that. We have our Niagara data arrays. We populate these in order to be able to pass data to the particle system. We have the path to our Niagara component. We have our system pointer and our component pointer, and then volume data and component. So here we have a T array of UN8. This forms the MIP data for our volume texture that we procedurally generate. Then we have our volume texture, and then we have our volumetric component. This volumetric component is just a static mesh component with a 1 by 1 by 1 box mesh with the minimum amount of polygons possible and inverted normals. That's it. So basically, we went in, we created a 1 by 1 by 1 box, centered pivot position, and inverted normals. These two values are used in parallax calculations. It's our last frame of reference location and our current frame of reference location. So this is where the camera was at last frame. This is where the camera is at this frame. And we use those to do our parallax effect. And then the only two, aside from setting these fields, the only value that we set, the only methods that we call externally is initialize to kick off our async initialization of the galaxy after we've set up um, our our values, like the parameters that we set top down, and then mark destroying that we need to call before we invoke destroy on the actor. So yeah, that's and then this is how we interact with it externally. This basically will change our initialization state to destroying, and we'll see later how that kind of affects the initialization logic. Then we've got our protected methods. We've got initialize data, fetch data, initialize Niagara, initialize volumetric, and try cleanup components and tick. So these are basically segmenting out our initialization process into discrete blocks of processing, and that allows us to like do a block, check if we need to destroy, if so dump out. It's basically like this allows us to separate out that logic so that we can short circuit it. So going over here, we can take a look at our initialize, or well, we'll just look here. So we're just setting up basically some root components and our Niagara component to begin with. It's actually our Niagara system that we generate. Um, then we have this initialize. So the first thing we're gonna do is we set up our first last frame of our first last frame of reference location so that we can begin processing parallax. Next up, we we populate or we construct our octree with the extent of our galaxy. And then we dispatch a task to the background to a background high priority thread. Um, we just have some logging here where I've been logging the start and finish time of all of our different steps of initialization. So first thing we do is we invoke initialize data, and then we have this line here. Um, if try cleanup components return. So try cleanup components is the next thing we'll look at here. This checks if our initialization state is not equal to destroying. So if destroy hasn't been invoked on this actor, then we're going to return false from this, which means that we won't return here. So as long as we're not in a destroying state, this return statement won't execute. If it does execute, then we're going to immediately dump out of this thread, and we don't need to do the rest of this, including setting our initialization state to ready at the end. The other thing this does is if it is destroying, we dispatch a thread to we dispatch a task to the game thread to basically destroy our volumetric and Niagara components if they're initialized. This solves the problem of them being like left over in the scene after our component was already destroyed. And then we return a true after we've dispatched that. And what that's going to do is cause us to dump out of our initialization process. So if I'm doing this and it takes a half a second, and then in that half second time, mark destroy is called, and we're set to destroying state. Then when we finish and we get to this stage, we're going to skip fetch data, initialize volumetric, initialize Niagara, and we're just going to immediately dump out. And that's kind of what the key change here that allowed this to work better is. That and dispatching it to the high priority background thread. Um, so that's how we're short circuiting. Mark destroying, all this is doing is just setting our initialization state to destroying so that when this gets called, it will not do this. It will not do this line, but instead invoke our destruction and return true. Um, so our different initialization functions have uh, different jobs basically. This function spawns a point cloud generator and then populates data into our octree using the point cloud generator and then finishes. So this is what generates the data. Then we fetch the data. So this is populating our data model, but because it's, because it's not 100% that like this will be one for one to generate one data point for every point that's generated. Like if you generated 2 points that overlapped at the lowest resolution of the octree, for example, then they would go in the same node. And so you would almost never like if I generate 2 million points, I would have like 1,999,973 points in the actual data model because of overlaps. So this is kind of this populates the data into the data model, and then we have to read that data back out of the data model with this get populated nodes. And again, this is all happening on the background thread. So fetching the data, we do a call to our octree to get all the populated nodes from our octree. We initialize our position, extent, and color arrays that we use for our point cloud or our Niagara system. And then we do a parallel for on a background priority thread to basically populate position, extent, and color from each of our node data from the nodes that we fetch from our octree. And then we log how long that took. And then the last two, initialize Niagara. This one's a little bit more complicated because it ping pongs between the game thread and the high priority thread. But basically, we're going to create a promise future because we want these to be synchronous, even though we want them to run asynchronously, but we want the method itself to be synchronous in the background thread that's running it. So all of these are following this promise. All these that are doing a separate game thread processing, following a promise future framework to allow us to make the overall function synchronous. So basically, we dispatch to the game thread. We generate our Niagara component because we have to call spawn system attached on the game thread. But we don't have to call set Niagara array data on the game thread. We can call this from a background thread. So we dispatch from inside the game thread that we just called to the background thread while passing through our completion promise. And we go ahead and we spawn, actually this data should actually be outside of here in the game thread. So I'm glad I saw that. Okay. Because these are trivial. The primary heavy loading that we're doing, the most expensive part are these array copies of these very large color, vector, and scale arrays. So after we've spawned our component, set our initial component, variables and such, we then dispatch back to the background thread to copy our array data into our Niagara component from our position, color, and extent array, which will be used by our Niagara system. And then finally, we dispatch back, after that's done on the background thread, we finally dispatch back to the game thread, activate our system, set our completion promise, and then we wait so that this whole thing is synchronous. Um, which means that up here, when we invoke this, it won't roll through to this line until this is done. Okay? All right, so that's initialize the Niagara system. That's our stars. And then initialize volumetric is the last thing we do. So basically, this is what does the gas. So we're gonna have a resolution here, which probably should move to an instance variable on the at the header level, as like volume resolution or something like that. I was doing 64. 32 made it just like trivially small to do this, and it still works pretty well. I could go back to 64 if I wanted a little bit, if I wanted like more fine detail in the base density map for the gas, but it didn't, like, honestly, it doesn't really seem to be necessary. And at 32, you're going from, let's see, calculator. You're going from 32 cubed um, samples to 64 cubed samples. So it's a pretty big jump. Like, where it's like, what, like three times 6 is 18, 21. It's like about 8 times more samples, roughly. Okay. So, and then we have one more early exit here in this, because after we've created this volume data, if we are destroying, we can dump out and we don't need to create the object. Which this part specifically, this line here and this line here are expensive. So if we don't, and they have to go on the game thread. So at least currently, I haven't figured out a good way to make this asynchronous for a volume texture. If it was a 2D texture, there's a paper I read that like I could use, but for a volume texture, this is the best way that I've found to do it, and there's no way to make this run off the game thread basically. Okay, so after we have generated our data and we're not destroying, we move on to the game thread. We dispatch a task. We create a new volume texture marked transient. We set up some various flags on the volume texture to do not compress, do not stream, unlink the streaming, and then just various like settings on this volume texture. And then we invoke this source init with resolution, 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 one MIP, this texture format. It's RGB 8, a alpha, red, green, blue, and alpha 8-bit. So that's 8-bit RGBA basically. And then the data payload from this texture data array that we fetched from up the line. So I think this is a definition. Yeah, T array of U and 8s. So we fetch its backing like raw array, and we feed that into the MIP data for this volume texture, and then we have to call update resource, which will compile that volume texture. And then finally, we just create our Galaxy Ray Marcher material, and then we set the texture parameter value for this volume texture. I'm not doing it yet, but the rest of the proceduralization for the material would go here. So things like setting, randomizing colors, randomizing the noise texture we use, things like that would go here. But I'm not doing that yet. Not worried about that. I'm more worried about getting everything buttoned up and tight and like performant before I go through that. The next thing we create our volumetric component, which is just a use, it's just a static mesh component. This is the like easiest part. Like none of this is complicated or difficult. Um, so we set our volumetric component. We set our static mesh to our unit box inverted normals. That's the cube I was talking about with inverted normals of size 111, center pivot. We set our world scale in 3D to 2 times our extent, which makes this match our octree dimensions. It'll make our unit box basically match the dimensions of our octree in our particle system. We attach it to our root component with snap to target, not including scale. We set its material to the dynamic material we spawned up here, which is where we would configure like the actual which is our that's how we would randomize like the way our gas appears, our colors, things like that. We register component, and then the last thing we do is invoke flush rendering commands to make sure that before we progress, like our volume texture initialization stuff finishes. Um, Finally, this is all just logging of the time it took to do that, and then setting the promised value, and then we wait on this completion future again, so that again this entire method, even though it's spawning an asynchronous task, is a synchronous method. Like it won't finish this method until the task is done, and that's fine to do because this task is not running on the game thread. This task is running on the background thread. Finally, tick is doing our parallax computation. We calculate our parallax ratio as our universe speed scale over our unit scale. We set with our actor origin to zero vector, but if we ever want to do origin rebasing, which we will need to update this logic to account for that. Um, our player offset equals our current frame of reference location minus our last frame of reference. And this is just the calculation for um, parallax. So current frame of reference location minus our last frame of reference location. So every frame we're checking the difference in our player camera location from this frame to the last frame. Then after we've calculated this offset, we can update our last frame of reference location to our current. Finally, parallax offset equals our player offset times 1 minus the parallax ratio that we calculated up here. And then we set our actor location to our current location plus our parallax offset, and then we invoke SuperTech. So that's it. That is the changes. I like it quite a bit. It's nice and clean. Our initialized method is clean. Everything makes sense. I'm going to eventually be porting this logic over to the universe actor, um, because it's like still in its original non-optimized mode. It's not as important because like having to wait 5 to 10 seconds for like the entire universe to load at the start of the game is not as big of a deal as having to wait 3 or 4 seconds to load every time you pass by a galaxy and it has to spawn in. But yeah, so those are the changes I made. Um, the components I had to build for this, if we go and take a look, oops, let's do this. If we go and take a look at the components I have a of a number of little components that I had to build for this thing to work. So first we have our empty universe ray marcher. We also have like a couple of examples. Like these were ones that I built as basically examples to build off of. But this is the one that's doing our volumetrics, and we have two instances of this. We have Universe Ray March instance and Galaxy Ray March instance. Galaxy Ray March instance is loading this material instance right here, which is just a variant or an instance of this original Ray Marcher. I'll probably change the name of this to like Nebula Ray March or something like that, because it's not universe specific. But then we have Universe Ray March, which is what the overall universe is loading. But the one that we're concerned about for this galaxy update stuff is right here. This ray marcher is marching this volume. This was an example of how to do this as a 2D slice, which I may eventually still want to move through to because if we do that, we would be able to harness uh, we would be able to generate our data into a texture 2D instead of a texture 3D, which doesn't sound like it'd be a big deal. It sounds like it'd be ideal to generate it into a texture 3D. Um, but there aren't the same RHI like graphics hooks for the 3D texture as there are on the 2D texture, and that blocks us from being able to asynchronously update these textures. That's why that I had to call that init and update on the game thread for the texture generation, which is really our only remaining visible hitch is when that stalls out a little bit. So it is possible that I may move to generating my textures into 2D textures instead of volume textures with slices. Um, but it's working pretty well now, so I'm not super concerned with it. So this ray marcher, I'll go into that at some point. I don't want to bog down into the weeds. Like if you check my GitHub, you can see the HLSL code that's doing this and the material and all that good stuff. But I'll probably go into this specifically at some point because this could be like a whole like overview in and of itself. Um, we have that. We have this unit box inverted normals mesh, which again is just a minimum geometry cube that has inverted normals. And we can look at that if I can get close enough to it and not lag out or okay, and what that means is what the inverted normals means is that when we're looking at this box, we're seeing the inside walls and not the outside walls, and that's really important because we're basically for our volumetric uh, gas, we're basically reverse ray marching from the intersection of the far wall back to the camera to do our ray marching for our volume. So like this is a super awesome technique. I also tried to convert my atmosphere to this, but it wasn't quite feasible to do it. I'm trying to remember what it was. Oh, I didn't have access to the same depth information that I have in a post process material. So in a post process material, I can take the world position node, and it will be the node of the actual world position intersect of from the camera. Whereas if I use the world position node in the context of a material on this, it will be the intersection with the box. And the depth buffer is non-linear, so you trying to do it from the depth buffer doesn't really work very well at the scales we're talking about. So the atmosphere will continue being a post-process effect because of that. But you can put a ray marcher on these inverted normal boxes, and it's actually really sweet. You don't need a post-process volume. You just need one of these box scale to house your effect, and you're good. Um, let's see what else. What other parts? Oh, the last piece of this. The only other thing that we're loading is this Niagara system, and it is very simple. We have some user exposed data, colors. Oh, I need to delete these out. Um, colors, ignore the 00. I was trying something. We have colors, extents, max extent, positions, and scales, arrays. So, array of colors, array of positions, array of scales, scalar value. And then our emitter state, self, once, fixed, 0, spawn burst instantaneous, 1, based on the count of our extents, which will match the count of all our other arrays. Spawn time 0, we just spawn a number of particles equal to the number of extents we have. And then initialize particle, we basically have this set up where color mode, direct set, select linear color from array, direct set, return particle ID, and then array sampling mode, direct set. Direct array index is derived from our particle's unique ID. Clamp, and our color selection array is our colors array, which makes sense. Position mode, direct set, select position from array, direct set, sampling mode, from our particle unique ID, from our positions array. Sprite attributes, sprite size mode, uniform sprite size, multiply float, scale times, select float from array, direct set, particle ID, extents. That's it. And then finally we have our particle update, which I can actually we don't have anything under particle update. We don't update our particles. We spawn them once, they live forever, and that's it. And then our sprite renderer, I have my star sprite material attached to this, which is just a sprite material that I've been slightly working on. It's just a basic, very basic. It faces the camera. That's it. So that's all this is, and this will spawn once all of this data is set, and then we invoke activate. That's right. So those are the three like actual like editor generated components that are used here, and then the rest is all C++. And we have our galaxy optimized galaxy spawning. I mean, it's not perfect, but it is better than it was by quite a bit. I want to address some of the like very standard looking um, distortion in my noise generators because I frequently get this distortion pattern. And also, we're going to want to add some randomization of like our domain position samples offset for our noise and our volume textures. So that's additional work, but this is kind of a proof of concept to show that we can use this, and I think I'm pretty happy with it. And again, like if we come over here, we go into a galaxy, and that little flicker at the start, like we will be able to fix that. I haven't really bothered with it. Like we can spawn the box as non-visible and then just flip it visible after we're done initializing our texture. That is all that the only reason that's happening is because of that. So I could go inside this universe or this galaxy here, and then if I were to reduce my speed to 0, let's say I found a star system that I wanted to put the player in. Let's say once we get close enough to a star system, this one here. Once we get close enough to a star system, let's say we transition the user from like universe and galaxy traveling mode, interstellar traveling mode to like inner system traveling mode, then we could, for instance, reduce our speed scale to 0. And now no matter how far I move, my skybox will stay the same. This is what our sky looks like in this neighborhood of the universe. And I am moving right now. I'm holding down the movement key, but our skybox is not moving. We're not traveling through space anymore. So like we could spawn in our planets and everything now and move between them without changing the way our like sky appears, like our relative position in the sky. And I'll ramp the speed back up. But yeah, that's pretty much it. Those are the changes I've made so far. Obviously, I still need proceduralization of like galaxy colors. There's some work on my point cloud generators where like when I'll show you the issue is like when they generate things that are right on the edge, we can get this kind of effect here. And that's just a matter of like tuning our point cloud generators to not um, generate data right on the edge of the octree. which is pretty trivial, so I haven't done it yet. It's just like now we just have a bunch of like kind of nitpicky, detailed things to work on. But yeah, I'm pretty happy with this. I think it looks cool. I think the volumetric effect is really nice. The volumetric effect is actually quite efficient because we're not doing any kind of like shadowing or light traces. We're only doing a density trace, um, which is much more efficient than doing a light trace. It wouldn't be good for like rendering a cloud or a or a nebula wrapped around a star that has like shading. But I have another component in mind for that. The heterogeneous volume is what I would use for that. For like local space nebulas that I want to be affected by lighting. For this though, for the purposes of just like creating interesting sky background, I'm pretty happy with the volumetric effects I have here. Um, and yeah, that's pretty much it. It's a quick demo of, you know, what I've been working on as far as optimization goes. The final kind of setup of the Galaxy actor that I'm going to use as kind of a template for the generation of the universe as well. And our ability to kind of just fly around at will and not have to worry about like it chugging whenever we pass by too close to a star, or like spawning in a galaxy at the origin and never being able to attach it to its parent actor so it doesn't get any parallax movement and it's just permanently orphaned. Ooh, that's a cool one. That's a pretty neat little galaxy there. I think once we get the proceduralization hooks back into the material for the interstellar dust in the galaxy, so that we get different colors and noise patterns and levels of distortion and scales of distortion and things like that attached to our galaxies, we'll get even more variance out of it. But yeah, I think that's it for now. Later.